All right, let's get started. It's my great pleasure to have Professor Evelyn visiting us today. Some of you might be in James Owen's talk on Monday, so we also make use of, we try to invite Eve Lee after the Shanghai conference to visit us. So Eve finished her PhD at UC Berkeley in planetary sciences.
No, astronomy.
Oh, in astronomy, sorry.
Yeah, no worries.
Yeah, in 2017.
Mm-hmm.
Yeah, and soon afterwards she started her faculty position at McGill, and recently she moved to UC San Diego as associate professor. She is a theorist working broadly on the star and planet formation, and also contributes a lot about the evolution of planets, how to explain the radius distribution we observed in exoplanet populations, which are critical in they're very active in understanding planets in general. So really excited to your talk today, and take it away.
All right. All right, thanks, Shami, for the intro, and thanks for having me here. If I look tired, it's because I actually am tired. I just flew in from Beijing, like just now, and I have very little sleep. I'm going to try my best to stay awake, but it also means that just feel free to ask me questions as well. Feel free to interrupt since the crowd is small. So I think it's gonna be better for all of us. Okay, so as Shami said, I'm a theorist. I work on a broad range of topics under sort of the umbrella of planet formation. And I will start pretty broadly before I dive into specific topics that I would like to focus on, since this is a colloquium. So let me start with the sort of history of the discovery of exoplanets, because like many other astronomy fields, this is very much a discovery-driven field. And for those of you who may know or may not know, the very first discovery of an exoplanet is actually not on this plot. You can get this publicly from NASA Exoplanet Archive. For some reason, the very first one is not on here. And I always like to bring that up because it was made by Canadian astronomers. I'm Canadian, and I remain a proud Canadian. So the very first detection of an exoplanet was made in 1988. And that was a cold Jupiter within a binary system, which made the discovery particularly tricky. But you can just imagine how much sort of like a pushback from the community, the general astronomy community, that they may have gotten, because we're trying to detect the signal of a planet around a star, and their mass ratios are like millionth, and the radius ratio can go down to like 100th. So it's really hard to detect the signature of these planets, and they did get a lot of pushback there. It just didn't get enough spotlight, and it wasn't until the early 2000s where the completely different group went back and verified that indeed this really was a true exoplanet. But it's a bit of a sad story, because the authors of the more junior authors of that paper could actually not get a job and actually moved out of the field. One of them actually decided to had such a bad time that they decided to destroy all the data afterwards, and it was just a very sad story.
Is it the pulsar exoplanets?
No, this is radial velocity, so it is just within a binary system, but it's a normal star. Yeah, so the pulsar planets are after this, and usually that's quoted to be the very first, but it isn't. This is the very first one. Unfortunately, it was just not the right time. So probably the discovery that everyone have heard about is the one that won the Nobel Prize in Physics in 2019. And as Shami is referring to, there were other discoveries in between, which was a planet around pulsars, which are compact objects, so not even star. So the reason why this particular discovery won the Nobel Prize is, as per their citation, it's because this is the first detection of an exoplanet around a sun-like star. And why is sun-like star important? Well, that's important because we happen to be orbiting around the sun. So now we're really getting to the question of, are there sort of solar system analog, like looking like further out, sort of like what does that tell us about the habitability of planets, for example? Except this particular planet looked nothing like what we see in our solar system because it was a hot Jupiter. And from then on, we see the gradual increase in the number of detected exoplanets. What really revolutionized this field, though, I would say, is the launch of the Kepler Space Telescope by NASA. And the reason why this was so revolutionary is because first it found thousands and thousands and thousands of planets. So you will see that the green over here is radial velocity. This is what found a lot of the first ever planets. But by and large, like orders of magnitude more, it's found by transit, which was using the Kepler Space Telescope. So having this huge number of exoplanet discoveries is important because now we have a statistically significant sample to identify some patterns, some trends, and really place our own solar system in the larger context. But it's not just the fact that it found so many planets, it's actually the fact that if the majority of the planets that the telescope found were unexpected. So prior to Kepler, theorists thought that this is sort of how the planetary population should look like. So mass versus orbital semi-major axis. And this is like population synthesis model, just plug in like all the different physics that we think is going on in the creation and the evolution of planetary systems and see what happens in the end. So the theorists back then thought that we should have a lot of rocket planets, a lot of gas giants, and nothing in between. Except Kepler, post-Kepler, turns out a lot of the planets actually fill up that gap, like right in between. So we now know that that gap doesn't exist, and in fact, it's a bit hard to see here, and that's because it's in mass. But 80% of the discovered planets actually fall right in between. So that really motivated the theorists to go back to sort of the drawing board to think again about like what did people miss? Like what physical mechanisms have we missed? And how can we understand like all this data coming from the Kepler Space Telescope to explain this unexpected population? And let me zoom out a bit and give you sort of a relatively current, I mean, it's 2021. This is a field where if you're off by just like 1 year, there's a lot of updates. But this is sort of relatively current census of the exoplanets, color-coded with respect to the different detection methods. Let me just go over the 4 major detection methods. I am not going to talk about astrometry, which actually is going to be pretty exciting with the Gaia, with the latest data release, but I'm not going to talk about that in this discussion. I'll focus on the other 4. So the first one is radial velocity, given in the orange circles over here. So this, as I said before, this is a detection that people have used to find those first ever planets. So what's going on? Well, the planet is orbiting around the star. Planet has some mass, so that's going to cause a displacement of the center of mass from the center of the star, and both the star and the planet is orbiting around the center of mass. So that orbital motion of the star can be traced with the blue shift and the red shift of the lines in the stellar spectra. And the degree of the shift tells us the mass ratio and the orbital distance of the planet. Now, the blue points, which labeled as Kepler, this is a transit method. Transit method tells us something different. So what we're doing here is we monitor the brightness of sample of stars. And for a given star, if we see a periodic dips in their light curves, that's due to the planet orbiting around and blocking our line of sight that causes the dip in the light curve. The frequency of the dip gives us the orbital period of the planet, and the degree, sort of the depth of this dip, gives us the relative size of the planet with respect to the star. So radial velocity gives us the mass, the transit gives us the size. And just to give you an idea, and you've already seen this in the cumulative discovery plot, by far we do have a lot more radius measurements than the mass measurements. This is more difficult. So I would say like 10% of this population also has the mass measurements. Okay, so radial velocity and transit, they're both biased towards shorter orbital periods. Like this region is much easier to detect. Farther out we go, though, it becomes very difficult to detect those with these two methods. We have to use different kinds of methods. Very, very far out, we can use what's called the direct imaging. Unlike the radial velocity and transit, which are sort of indirect methods, direct imaging, you literally just take picture of the planets. These are self-luminous planets. We're taking the thermal emission from the planets, so the planets have to be massive, and they have to be young, and they have to be far away from the star so that we can actually resolve their signal. So that's why the imaging is all the way at the top over here. Now you take a look at this and compare this with the solar system planets, and you'll note that there's a very blank spot over here where the solar system planets lie, and that's because we just happen to be living in a system where there are small planets far away from the star, and currently it's just impossible to detect the true solar system analog. But there is another method that is uniquely capable of probing this region, and that is microlensing. So this is gravitational lensing effect. You just look at some dense stellar fields towards the galactic bulge, and the foreground object, let's say a star, can lens the background light source, and that's going to cause magnification. But let's say that foreground star is being orbited by a planet. Planet has mass. It's going to cause a secondary lens. So there's a little deviation. We can use that to get an idea of the mass ratio and also the orbital semi-major axis of this planet. So this method is uniquely capable of going all the way down to Mars-sized objects at intermediate orbital distances. That is impossible with any other detection methods. So I'm super excited about this. There's a NASA mission. Fingers crossed it'll actually launch, but it should. There's a NASA mission, the Roman Space Telescope, that is expected to be launched next year, that is going to do exactly this. So as a theorist, I'm particularly excited about the possibility to fill up this space, not just because we have like a better, sort of more complete picture of how planets form and evolve, but because this is exactly the region of this parameter space where you need to probe to test a lot of the formation theories. All right, but for now, let's take a look at where most of the data lie, which are short orbital periods. And also, let's take a look at size of the planets, because that's also where we have most of the data. So going from left to right, we're going from small to large, and small usually correspond to rocky planets, large usually corresponds to the gas giants. So this is where the Earth and Neptune correspond to, and in our solar system there is nothing over here, which is why initially the theorists thought that this should be the same, that there should be nothing over here in the extrasolar planetary system as well. But as you can see, there's quite a bit of planets over here, and in fact it really dominates. But take a look at this, and you'll see that this is not a flat distribution. There are some features. One feature that is quite prominently discussed in the field is this radius valley. It looks really small, but it's actually statistically very significant. It looks small because I'm plotting in the log space. And then there is a peak over here that people call as mini Neptunes or sub-Neptunes. I'll use those two terms interchangeably in this discussion. And once you go beyond around 3-ish Earth radii, then there is a drop-off, the radius cliff, drop-off by about an order of magnitude. Overall, our galaxy tends to produce a lot more small planets than the large planets. And there are also all these different features. So how do we explain this? Why is it that we have many more small planets, and why is it that it is not a flat distribution within those small planet population? So I'm going to approach this from the formation perspective, and I believe everyone here knows this, but let me just set up the picture. So in this discussion, I'm not going to talk about solid coagulation phase at all. That deserves a completely different talk. I'm not going to talk about that. I'm going to assume that we were successful in creating already a solid rock. And the solid rock is massive enough that it can start to accrete the gas that is in the protoplanetary disk and form the planetary atmosphere. Something that is important to keep in mind in planet formation is that there's a time limit because the disk is evolving. On the outskirts, the gas gets blown away by wind, so that's either MHD driven or from photoevaporation. On the inside, the gas gets accreted onto the star. We can actually observe this at short wavelengths. So overall, the disk gas goes away within a few million-year timescale. So creating a planet, especially those with an atmosphere, means that has to be completed. It has to complete within a few million years. All right, so let's now talk about the physics of gas accretion. And as before, we already have this rock. It is embedded in gaseous nebula, so it will accrete gas, sort of bind the gas, gravitationally bind the gas within its heliosphere, bondisphere if the bondisphere is smaller, but at these orbital distances for the sub-Neptune masses, it's actually helioradius that's relevant. So it binds the gas within the helioradius, but then the binding process, it's a release of gravitational potential energy. So it's going to heat up the gas closer to this rock and establish a temperature gradient. And nature doesn't like having any sort of gradient, right? Like it's going to try to erase that by cooling off this gas layer. And the gas layer that is cooling off is going to shrink, but you still have this heliosphere, so that allows for more gas to refill the heliosphere of this planet. So that is the heuristic picture of how a planet builds its gaseous atmosphere over time. If we want to quantify this, we do need to know the thermal structure of this envelope. Until relatively recently, the idea was that it is largely a two-layer structure with the outer radiative zone and the inner convective zone. Recently, about 5 years ago or so, there has been a three-dimensional numerical hydro simulation that found that actually the outermost layer may be advective, which means the gas from the disk comes in and cycles out over a local orbital time. What we find in my group is that, yes, that layer exists, but it is thermally unimportant, so it doesn't matter in terms of the atmospheric growth. And I'll tell you in a bit why is it that it is thermally unimportant. But for now, let's ignore this advective part, and let's just focus on radiation and convection. So why this particular order? Why convection in the center? And that has everything to do with opacity. So remember, all of this accretion by cooling is happening because of the temperature gradient. To give you some numbers, all the way at the bottom, it goes up to about 10 to 20,000 Kelvin. And at the top, it meets the disk temperature, which is about a few hundred to 1,000 Kelvin, depending on how close you are from the star. So as you go deeper and deeper, eventually you're going to hit a temperature of about 2,500 Kelvin. And 2,500 Kelvin is a special number because that's when you can thermally dissociate hydrogen molecules. So you thermally dissociate hydrogen molecules, you have some free hydrogen atoms, and you're always going to have some trace amount of free electrons that got off the outermost valence shell of metallic species. So you're going to have H- ions. And H- ions are more likely to get rid of the extra electron by absorbing the thermal photons. So if you take a look at the opacity grids, then it's the H- ions that dominate the opacity from the dissociation front of the H2 molecules. And H- opacity is a really, really steep function of temperature, so it just makes the entire inner envelope extremely optically thick. So it's just prohibitive to transport energy by radiation, so convection prevails instead. Another consequence of H2 molecule dissociation is that requires energy because it's a thermal dissociation. So that thermal energy, instead of populating the translational modes of the gas species, it goes into dissociation of H2 molecules. So what does that do? Well, it sort of causes like an isothermal effect. What that means is the adiabatic gradient shrinks, and that effectively causes inwardly concentrated mass. So more than 80% of all the gas envelope is actually locked into this convective zone, and in particular, it is centrally concentrated towards the bottom of the envelope. Yeah?
What's the order of magnitude of the advective motion? Do we expect shocks to occur?
No. So it's about a local orbital time.
Okay.
Yeah. So like if it's the Hugh radius that dominates, then it's gonna be slightly subsonic, like transonic.
Okay.
Yeah.
And there are like hydrodynamic flows from accretion.
Yeah.
That drives the.
Yeah. So it's the gravitational potential of the core.
Okay.
Yeah. Yeah. So actually, this thermally unimportant part, it depends on like how far this flow can go in. So if it actually approaches all the way down to this radial convective boundary, then it does become important. But if you do careful like radiation hydro simulations, you do not see that. Like it sort of stays upwards. Okay, so sort of alluding to that, why did I mention radial convective boundary? Because the layer in which it actually is relevant for the thermodynamics is going to be relevant, is going to be related to this inner convective zone. And when it comes to convective energy transport, it's all mediated by the boundary conditions. So the thermally important layer is actually going to be this radiated convective boundary. So why is that? Well, like I can go through the I can show you formulas as to explain why. But instead, I'm going to show you a demo that demonstrates this. This is a relatively simple demo that I made a long time ago as a grad student at Berkeley. This was for a donor event. But it really is relatively simple. It just used tea, cream, and an ice cube. So I'm gonna play it. So this is hot tea, and I'm pouring cream so that I can use it as a tracer of convection. And right now, because I poured the cream is actually going through the sloshing motion. Just basically the surface gravity waves. That's not convection, so I need to let it die down first. So once it settles down, I'm putting metallic lid on top of this fluid layer so that I can easily change the temperature at the top by placing ice cubes. So I just placed one. That's the second one. It already does something. It already creates a pretty global mixing, and at the time I couldn't see what was going on, so I put the third ice cube. And that should really speed up the process. Like you'll see that like there's a lot of activity, like a lot more eddies going there. And then within seconds you have a complete tea cream mixture, all by putting ice cubes on top. All right, yeah, so this is sort of a simple demo that you can check for yourself that, like when it comes to convective energy transport, really what matters is like what's happening. So thermodynamic properties like right at the top layer. And this makes sense because what have I done here? I've effectively steepened the temperature gradient, which is a criterion for the triggering of convective instability.
So that gas accretion won't happen, can happen spherically. It won't make like this kind of thing, like a star formation.
Yeah. So there is so this assumes spherical symmetry, but in reality, it's not quite symmetric. So the accretion flow itself, the hydrodynamically, is actually polar. And there's a bit of so this recycling flow and something that comes out, that's actually on the equatorial region. Yeah. But it's still a bit unclear like what the loading factor is. Yeah, and the reason why that is not clear is because it's really hard to resolve this entire thermal structure in the radiative hydro simulations, unfortunately. All right, so in this picture, all we need to know is the thermodynamic properties right at this radiated convective boundary, but I actually know that already because I know this transition occurs at the hydrogen molecule dissociation front, and that happens at 2500 Kelvin. So using that, I can write down analytically the growth of the envelope mass as a function of the time that was allotted for the accretion of this atmosphere, how massive this rock was, and also the elemental, basically metallicity of the gas that it has accreted. So the more time you have, obviously you can create the thicker atmosphere. The less metals you have, the more optically thin the envelope becomes, so it's going to be easier to cool. That's why it's inverse. But by far it is the mass of this rock over here to which this envelope mass is most sensitive. And again, that is because of that strong central mass concentration due to the hydrogen molecule dissociation. So that's where the strong dependence comes from, and that is why this entire process is rather insensitive to what is happening all the way at the very, very outer boundary. Like it's more sensitive to what is going on in the deep interior. So if we just take this and do the calculation over a wide range of parameter space, so a range of the rock mass, and as a function of different times, different accretion time, then this is what you get. So this is the expected envelope mass fraction. The thicker envelope you have, obviously you're going to become gas giant. And intermediate, you have the sub-Neptunes. And for a reference, Earth is down here. So staring at this, we already kind of can tell why is it that our nature prefers the creation of the small planets over the large planets. The large planets just occupy a very, very small, tiny region in this parameter space. It's just really hard to create them compared to the small planets where there's a lot more allowance for the creation of the small planets. So that's probably why we see a lot more small planets than the large planets. Now, if we take a look at this very clean upper envelope, this region over here is coming from the thermodynamics that we've been discussing, but you'll see that at the ends, there are some different behavior. So for the high mass end, actually thermodynamics no longer applies, and instead it switches to hydrodynamics. That happens when the envelope mass becomes comparable to the core mass. Then now the self-gravity of the envelope becomes important, and the cooling time scale to maintain that envelope in hydrostatic equilibrium gets really, really short. Like so short that it's no longer thermodynamics that's limiting the gas accretion. Rather, it's the hydrodynamic delivery of the material towards the vicinity of the planet. That's why there's a switch, but I'm not going to talk too much about that. Instead, I like to focus on what's happening over here, because this is going to give us the radius valley. Okay, so what's going on over here? Why the fall off? So this fall off occurs not because thermodynamics doesn't happen. It's actually sort of the end state of this thermodynamic process. So remember, all this cooling is occurring because there's a temperature gradient. So the cooling process itself is a tendency for the system to get rid of the temperature gradient. So once you have erased that temperature gradient, you are done. So you're done cooling, so you're going to stop your accretion. So that's what's going on here. These masses are so light that you very quickly reach this isothermal maximal state. And because that is exponentially sensitive to the core mass, we have a steep drop-off. And this is what's going to give us that primordially the radius valley that we have seen in the data. So to see that more clearly, let me just clean up the same plot that we were seeing. This is just a cleaned up version where I am just drawing at individual epochs in the disk evolution. So again, we have this very steep drop up over here. So looking at this, even if we have a very broad underlying core mass distribution, the size of the planets that would be consistent with these range of the envelope mass fraction would be much less numerous because there's just not enough dynamic range. So if we do that exercise, then this is what we get. If you're wondering how I go from the envelope mass fraction to the radius, there's almost one-to-one correlation between the two. This is what is observable. That is what theorists can calculate from formation, and there's almost one-to-one relation. So as I've explained, there's this gap over here. Because of that steep drop-off, you just can't populate this space anymore. And the reason why it goes back up is because once the envelope mass fraction falls below 10 to negative 5, then the atmosphere is just so thin that the size of the planet is governed by the size of the rock itself. So that's why it goes back up. But it's quite remarkable that this does give you, at the right location of where the radius valley is, that we see in the data. So how does this compare with another sort of observation of phase space that people like to look at in terms of explaining this radius valley, which is size versus orbital period? So initially, people, for some reason, thought that this gas accretion process should give you the wrong kind of shape in this radius valley. So it's a bit hard to see here, and there are many different versions of this, but generally speaking, you have this valley, and if you actually sort of like fit a line through the data, it goes in the negative sense. So the valley, the valley itself goes to smaller radius the farther out you go from the star. And people thought that, oh, gas accretion should give you the opposite kind of slope. Well, actually, it does not. It will give you the exact same negative kind of slope. And in fact, this value agrees with the data very well within 1 sigma. So why is it that the gas accretion process does give you this negative slope? And the reason for that is when you're going closer and closer towards the star, the disk gets hotter. And if the disk is hotter, then it's much harder to gravitationally bind the more thermally energetic gas species. So your binding radius shrinks. That effectively shrinks the isothermal maximum mass, and that will shift the transition from the cooling curve to the isothermal curve to the larger mass of the rock, which would correspond to the larger radius, larger value of the radius gap. All right, skip that. Okay, so formation already gives you this radius value that is in very good agreement with the current data. But remember, earlier in this discussion, I've mentioned how there's a time limit to planet formation, and that's about a few million years. So ages, the typical ages of the planetary systems that we observe is more like a few gigayears. So that's quite a bit of a jump in time scale. There are a lot of things that can happen, especially for the short period planets. These planets would be affected by the host star from that few million year formation to a few gigayear evolution. So what kind of star-planet interaction is relevant? First is photoevaporation, which I would just like to mention that this was the first theory that was used to predict the existence of the radius valley. And the basic idea is that the X-ray and UV photons from the central star, it hits the planet atmosphere and ionizes the upper layer, and the free electrons thermalizes the surrounding gas, and it drives off the wind as it heats up the gas. And that can cause a pretty effective amount of mass loss. When you're, this will operate out to about 50 days or so. When you're closer in, like 3 days around the star, then now you have to worry about tidal interaction between the star and the planet. If you're even closer in, like less than a day, then now you have to consider electromagnetism. So let me start with photoevaporation. So I've already mentioned like the basic idea behind photoevaporation, and it would manifest as transforming the short period gas envelopes of Neptunes into the rocky planets. So here what I'm doing is I'm taking the formation population that I've mentioned before, where you already just out of formation create this radius valley and just let it undergo photoevaporation, because actually physically speaking it's actually really hard to shut that off. So we're just going to see what happens, and essentially it actually maintains the radius valley pretty well. It does cause a little bit of a changes at the edges, but largely speaking it's almost like a second order effect. So from my perspective, the more interesting question is like, what are the parameter space, or what are the region of the parameter space where we can cleanly probe the formation physics rather than like photoevaporation. So first of all, when we take a look at mass versus radius and focus on where the current super Earths or rocky planet population lie in this diagram, they're actually way too massive that they must have been photoevaporated. And that actually makes sense because these are small objects. They're actually at really, really short orbital periods. You do expect them to just lose all their atmospheres over time. So in order to cleanly probe formation physics, we do have to go beyond, like well beyond the 50 days, maybe even 100 days, like if the star has a particularly high UV and X-ray luminosity. So I'm particularly excited about missions that can probe this long period rocky planet population. On the US side, I've already talked about the Roman Space Telescope that will give us the sort of mass distribution at this intermediate distances. European mission Plato should also be able to do that. And I believe there's some really exciting space telescope planned in Asia as well. All right. So looking at the radius versus the orbital period diagram here, there is a gap between the two populations, which is probably carved out initially by a purely gas accretion process and further carved out by photoevaporation. Now if we go even deeper, around a day or so, there are this population of planets that people call ultra short period planets. Those are planets with periods less than around a day or so. I think the lighting, maybe you can see it. There's an upper edge and the left edge over here. You'll notice how the upper edge does not continue the evaporation trend. It actually flips, which means that there's something else going on. There's a different physics going on. So let's take a look at the remaining two star-planet interaction physics that I've mentioned before. So let's first talk about tides. So when it comes to tides, there are two tides to consider. There's stellar tides, so tides being raised on the star by the planet. There's tides being raised on the planet by the star. The latter is more important if the planet's orbit is has an eccentricity. Like even with like 0.1%, like it would matter. But when you have that eccentricity, it can pretty effectively be damped away over a pretty short time scale. So in this discussion, I'm only going to consider tides being raised on the star by the planet that's going to cause a tidal orbital decay of the planet. Few things to keep in mind. Because this is such a small planet, the time scale of this process is rather long. So think a few to like even tens of gigayears. So most of the time the star is going to be on main sequence. So it would have been spun down. So the spin period is going to be greater than a day, so orbital period of the planet. So that means the planet has higher specific angular momentum. It's going to transfer its angular momentum to the spin of the star. Also, the tidal bulge that is being raised on the star by the planet is going to lag behind because of some friction inside the star. And I say friction because it's still not well known from first principle physics of what exactly is causing that dissipation. All right. So in this tidal interaction, the end point is for the system to reach some kind of equilibrium, as nature would have it. But for star-planet system, that is never going to happen because the planet is just so much lighter than the star. So the total spin angular momentum of the star basically acts as an angular momentum bath. So the planet will just continue to lose its angular momentum and spiral down until it reaches a Roche radius and be destroyed. We can write down the tidal orbital decay rate, and the tidal Q parameter over here is where we just hide all the uncertain physics of dissipation. But what I'd like to argue is that these small planets are ideal sites to constrain this tidal physics in terms of, or as a function of stellar type. Much more so than hot Jupiters, and that's because these small planets appear over a much wider range of the stellar types. So we're going from right to left, higher mass star to the lower mass star, and different stars, depending on their masses, would have different internal structure. So higher mass stars would have a much thinner outer convective layer. Lower mass stars would have thicker and thicker until fully convective structure. And we generally think it's within this convective layer where the G modes decay. So we generally expect stronger tidal dissipation when you have a thicker convective layer. So how does that bear out in the data? So if we just apply that tidal decay rate and draw a sort of like a survival edge. So if you're above this line, the planet should not exist basically because it would have just spiraled down to the Roche radius. Does pretty good job, actually really good job for the sun-like stars and K-dwarfs, but we have some issue for the early to mid-Ms and the late Ms. So we're having a problem because in this simple exercise, I've assumed the tidal Q parameter to be just constant, just fixed, regardless of the stellar type. But the data model comparison, I think it's already telling us that that is not true. In order to bring the data in closer agreement, in order to bring the model into closer agreement, we do need higher level of dissipation for the early to mid-Ms and the late Ms. And in order to do this at a quantitative level, I unfortunately do need more mass measurements. So it's only the black points where we have precise enough mass. The magenta points are the ones where we don't have any mass measurements. I really hope, I'm trying to motivate my RV colleagues to follow up and get more mass measurements of this ultra short period planets. Okay, so if you go back to this diagram and draw the survival line due to the tides, it does a really good job at getting that upper edge of that USP population. Now, what about this left edge? And this is relevant for planets that are very small. So these are planets that are less than around an Earth mass. At that point, it's so light that tides is so ineffective that it doesn't really matter. And you're also very close into the star. And at that point, electromagnetism matters. So stars have magnetic fields. Younger stars are more at higher level of magnetic field intensity. So as the planet orbits around the star, it's going to pluck along the magnetic field lines. And the plucking is it's a perturbation. So a perturbation means it's going to drive waves. It's going to drive Alfvén waves. And furthermore, because the planet is spatially localized and it's orbiting, it's going to cause a time variability in the local magnetic fields. And time variable magnetic field induces electric field. So, and it's going to drive current. So this sketch is relevant for polarity of the field lines such that it goes downward. Then use your right-hand rule, and you'll find that the current goes this way, and it follows the field lines, land on the star, comes back out, and land back on the planet. This does assume that the planet has some conductivity. So this sketch assumes that we do have a closed circuit loop. That's not always, that's not guaranteed, but actually it is guaranteed for the ultra short period planets, because the condition that we need is for the alpha velocity, so that's the propagation speed of that perturbation in the magnetic field. That has to be greater than the orbital speed of the planet, because this is the perturbation, like the speed at which you drive the perturbation. The information has to have enough time to travel down to the star to maintain the causal connection. Another way to think about this is, as long as this is true, you're going to have a minimal level of twist in the field. Otherwise, you're going to break the field completely. All right, so otherwise, same thing as before. The star is spinning more slowly than the planet's orbit, so the planet is losing its orbital angular momentum to the stellar spin. You'll notice that, like, I have the resistor label over here. That's because both the planet and the star do act as resistors. So this is just resistor circuit, and probably from your experience with the electronics, they do heat up through the resistors. So we call them as the Joule heating. So the entire system is losing energy through this Joule heating. And you can actually write this rate on an order of magnitude fashion. So start with the Joule heating. It's just the induced potential times the induced current. We can write down the induced potential from the electromotive force, and the current we can derive from the Maxwell's equations. So we just combine everything together, and this is the expression you end up with in the end. So just to break this down, this is the magnetic energy density or magnetic pressure. Notice how it's the perturbed component of the magnetic fields. The cross-sectional area of the perturber times the alpha speed, which is the propagation speed of this perturbation. All right, so you apply that to the orbital decay rate, and again, same thing as before. This is a survival line against the magnetic orbital decay down to the Roche slope radius, where the different blue curves correspond to different stellar magnetic field intensity. Again, does a really good job at explaining the shape of the edge that we see in the data, except for these 3 points. What's going on with those 3 points? Well, those 3 planets happen to be orbiting around particularly slow rotating stars. And we know that slow rotating stars do have a systematically weaker magnetic fields. But as someone who works on exoplanets, I'm actually quite excited about the consequence of this magnetic drag on the planets. There are different possibilities. One thing that I'm super excited about is that if you can just tap into like 0.3 to 0.1% of that Joule heating and just put that into the planet, you can destroy the planet. It actually goes above the gravitational binding energy of these rocky planets. And this is exciting to me because this means these could be progenitors of the observed catastrophically disintegrating planets that we find in the transit light curves. But if you can actually destroy or not does depend on the actual thermal evolution of these planets. So instead, you may not destroy it, but the amount of heat flux that you would get from this magnetic orbital decay is on the order what is currently driving active volcanism on Io. So these could be a great place to look for the extrasolar volcanism. Yet another, maybe a slightly less exciting but still observable consequence is that maybe none of this happened and you reach some kind of radiative equilibrium, but that should be observable. So in order to test this, my student at UCSD, Vincent Savignac, is currently evolving the structure, the thermal structure evolution, including this Joule heating, radiative heating, and the cooling process all together. This is very much a work in progress, but just to give you an idea, the day side, it's all molten. The night side is much cooler, so this causes differences in how much of a Joule heating would be deposited depending on the day side versus night side and where you are on the night side actually. So what we're currently finding is that you sort of oscillate around the equilibrium point, the radiative equilibrium point, and you like oscillate between like a liquid state and the solid state. You just like keep going up and up and down. But anyways, this is a very much work in progress, so please stay tuned. All right, so to summarize, if we put back this magnetic drag line, then, sorry, it's a bit hard to see, but it really does a good job at getting the left edge that we see in this in the data right now. So depending on where you are in this parameter space, we are probing different kinds of physics. The farther out you go, we are probing the formation history. So another way to say this is if you want to probe formation history, you really do have to go farther out. Especially this currently blank spot over here. If we find, for example, if you find a lot of rocky planets beyond like 100 days or so, then it's actually a very strong evidence that this gap is initially carved out just purely from the gas accretion process. So again, I'm really looking forward to the missions that can probe this region. If you're closer into the star, that's not a good place to study formation, but it is a really great place to study star-planet interaction, including photoevaporation, but something that I'm more excited about is the opportunity to constrain the tidal physics as a function of stellar type with more mass measurement of the small rocky planets, and for even smaller objects at very short orbital periods, these could be progenitors of catastrophically disintegrating planets, or this could be a driving magnetic volcanism, which could be observed in the optical spectra for refractory species, or if you believe that there are some volatile species locked in, then we could target those with JWST. If instead of all of those you do reach the radiative equilibrium, then that could actually be observed in the Miri wavelength of JWST. So thermal phase curves then would be very, very informative. Thank you.
Thank you for the informative talks. I'm not familiar with the planet formation at all, actually, but I'm just curious. Based on your talk, the final characterization of the exoplanet is determined by the formation process and the evolution process.
That's right.
So, which part of the characterization can be determined by the formation process, and which part of the characterization can be determined by the evolution process? And also, I'm also wondering, how important is the initial condition like disk mass or size or different things for characterization?
Right. Yeah. So let me answer the first question first. I think the orbital period is basically very important in terms of formation versus evolution, because the problem with the short orbital periods is that there is way too many evolutionary physics going on that can completely erase away that initial conditions. The farther out you go, the more pristine the environment is, because none of this is going to happen there. So you don't have to worry about that. It's just you actually can retain that initial memory. So, and to your second question, in terms of how important is the sort of the disk processes, that's really important, which I just said, I'm not going to talk about it, is in the growth and the coagulation of the rock. Then it's actually becomes very important as to what's going on in disks.
So, why was there the belief that there were only two types of planets in the pre-Kepler? Why this theory think that has to be the case? Is there any theoretical motivation for that?
Yeah. To give these authors more credit, so that's Shigeru Ida and Douglin, to give them more credit, they actually explore a huge range of different initial conditions. And if you read their papers, they actually do have solutions where this does get filled up. But motivated by what we see in our solar system, because back then we didn't have this Kepler data, motivated by the solar system, they thought this was the most likely scenario.
I see.
Yeah.
But it's not because of some physical mechanism that prevent planet from.
Yeah, so in terms of a physical mechanism, this is mostly due to a disk migration.
Okay.
Yeah, so when you have a planet within the gas disk, then it, they tidally interact with each other, right? The planet and the gas, and it drives waves. For typical disks, that causes inward migration of the planet. And that is very efficient for planets sort of above, around an Earth mass, depending on where you started. So that can actually completely get rid of these population. Yeah, and pile up a lot of planets over here, which they've sort of just ignored here. But there are a lot of more modern version of this with different groups. And if you look at their papers with a very efficient standard disk migration, they will have a huge pileup of planets at the edge, for example, which we don't see in the data. Yeah.
Regarding geoheating, do you need the planets to have partially ionized gases, and does it matter if it's more of a gaseous planets versus rocky planets?
Yeah, so these planets are completely rocky. So we all it matters is conductivity of the rock itself, and whether it's molten versus mush versus a crust. We haven't considered atmosphere because it's just so close in. Mm-hmm. Atmosphere would be gone. Yeah, because these planets are less than 2 Earth radii. Yeah.
So speaking of which, if you go back to the radius period diagram, So above that, there's also a boundary that enclosing the Neptune desert. Can you talk a little bit about does type matters, or what would be the important physics to consider for that boundary? Yeah,
so that's this, right?
Yeah.
Yeah, so this is this.
Also going that way, right?
This and then that. Yeah. Yeah, so this can actually be driven by photoevaporation. So photoevaporation does this, but it also gets rid of these, right? Mm-hmm. Yeah, so this boundary can be explained by photoevaporation. Mm-hmm. And that's not photoevaporation, you can't do that, but you could do it dynamically with the high eccentricity migration. Yeah. And of course, right now, a lot of people are interested in those trace population that fill up the space. But I think those have a pretty high densities, so they are actually resistant against mass loss. Because there are now more discoveries of planets that populate the desert.
Okay. So Eve will be around until tomorrow. Yeah, and feel free to. So she'll be staying in TC's office. Yeah. Welcome to Chatter. Yeah. Thanks for the great talk.
Thank you.